It's a pleasure to be here, and it's great to see so many people out here. Before I start, I just wanted to point out this website over here that's connected to the cards you have, and it has some really nice videos that clearly explain global warming. So if you're interested, you can take a look at that. So I'm a cosmologist, and that means I'm interested in how matter and light is distributed on very, very large scales in the universe, and how these distributions change or evolve in time. And it's a very exciting time to be a cosmologist, and the reason for that is that we have many great telescopes, both on the ground and in space, and these are coming back with many great measurements that are reinforcing two very striking results. I mean, you've seen pictures from the Hubble Space Telescope and from the James Webb Telescope, and they're really, really beautiful, but they also have great scientific value. And one of the results that are being reinforced by these measurements is that when you look at the total energy budget of the universe at the present time, we only understand about 5% of the contribution that comes from atoms and molecules. And those are the things that make us up, and they make up elephants and blue whales and trees and planets and stars. The remaining 95% of the energy budget, it's divided into two parts. One part's called dark matter, and the other's called dark energy. And we don't understand almost anything about these two substances. We know that they produce gravitational fields because they have masses. And that's pretty much all we know, because we see that their gravitational fields affect other things that we can see directly. And that's why we know that there's dark energy and dark matter out there. The other result that these observations are reinforcing is that when we look at quantum mechanics or Einstein's theory of relativity, or even both of them, they're suggesting that both or possibly one or the other is incomplete and needs to be improved on to better the description of reality from a physical model. And if that holds up, that'll be very profound, because relativity and quantum mechanics have been the foundations of physics for over a century now. So let me start with this picture. This is a reserve outside the town I live in, and it's a restored grassland, and these are American bison, and it's a very nice place to go hiking. So I have some questions for the audience. So how many of you have gone hiking 10 kilometers in your life, integrated, total, cumulative? If you put up your hands. Okay, how many of you gone 100 kilometers in your life? So there's still a few, like 10 or 15 people. What about 1,000 kilometers? 1, 2, 3. Okay, what about 10,000 kilometers? Okay, so it's pretty clear that there's an upper limit to the distance you can probe directly. If you have enough time and you're old enough and you have nothing else to do, you could probably go 10,000 kilometers. Okay, let's go down to the other end. I want those of you who have hair to reach up and grab a strand of hair and feel it. So is that kind of the limit to which you can feel something small with your fingers? That's somewhere around the limit, right? So typical human hair has a diameter of maybe 100 microns. And in terms of meters, that's 10 to the minus 4 meters. So there's a direct limit to the length scales you can directly probe with your senses. And we can start up over here. So the length scales are up over here in meters. And if you're patient enough, you can maybe go 10 to the 5 meters or 10 to the 6 meters in your life. And if you have very sensitive fingers, you could probably feel down to 10 to the minus 4 meters. But there's a lot going on in the real world on much, much larger scales and much, much smaller scales. And this is a logarithmic plot, so it's powers. So it's 10 to the 5, 10 to the 10, 10 to the 15. And it's a very big difference when you go from 10 to the 5 to 10 to the 10. So it's a huge range of scales here. So there's a fundamental difference between how we build up intuition about reality on these scales, then we build them up on these scales and on these scales. So if you're very clever like Newton, you can take balls and collide them, and you can figure out that energy is conserved and momentum's conserved, and you can drop apples, and you can figure out the inverse square law of gravity. But that's what's known as Newtonian physics. But when you get out to very, very large length scales, you cannot directly access them through your senses, and you can't do that on really tiny scales either. You can't feel atoms, you can't feel neutrons and protons and electrons. And the way you develop intuition up here and up here is very different than the way you develop intuition over these length scales. So what you have to do up here, for example, is you take a telescope and you point it at something you're interested in, like a star or a planet or a galaxy, and you collect that light. And nowadays, you can focus that onto a CCD and turn it into electronic signal, and you store it in your computer. And then you go and build a mathematical model of that planet or star or galaxy, and you heat it up or do whatever it's doing and see what colors of light it emits and see if it agrees with what you store in your computer. And if it does agree, then you can kind of appreciate that your mathematical model provides some description that agrees with what's real out there. And then you try to improve your mathematical model by maybe introducing a few more parameters and make it more sophisticated and try to get better observations. And you build up intuition that way. And the same thing happens down here on much smaller scales. So what you do is you use a microscope or you use a particle accelerator. But you cannot directly access those length scales or those length scales with your senses. And so maybe it's not that surprising when people discover that things out here behave very differently than things out here and things out here. And quantum mechanics is very important here, and relativity is very important here. And so maybe in that sense, people call these things unintuitive, or relativity and quantum mechanics are unintuitive. But that's just because you cannot directly access those length scales through your senses. And it's not usually appreciated how large a set of length scales are out here. And so I'm going to spend some time walking out over here. But if you're interested, there are two very nice videos. The one's called The Powers of 10, and it's by the Eames brothers. That's E-A-M-E-S. And if you search on a good website, a good search engine, you can find that. And they give a very good description of these different length scales. And the American Museum of Natural History also has a nice video, an updated version of that, and you can search a good search engine and find that. So what I'm going to do is I'm going to walk out, and we'll start out. So we can do this in terms of length scales. We can do this in terms of mass scales or time scales, and we don't have time for all of them. So I'm going to do this in terms of length scales, and I'm going to start with a different length scale than what you're used to. Some of you probably recognize this guy, and I'm going to use him as my length unit. So an Einstein is 2 meters roughly, and that's kind of a human scale. And then we're going to compare him to this object out here. These types of photographs have only become possible in the last 60 or 70 years since we've had satellites with cameras. And one thing we could try to do is to build a tunnel from the North Pole to the South Pole and build a base here. And then all you've got to do is go and collect 6.5 million Einsteins, put the first one at the South Pole, the next one on his shoulders, and the next one on his shoulders. And if you have 6.5 million of him, you'll cover the diameter of the Earth. And 6.5 million is roughly 10 million, so that's 10 to the 7. So to go from Einstein to this, it's a jump of 10 million or so. So we can do another jump and go to our nearby big star, which we call the sun, and do a similar sort of experiment, but it might be a little more difficult because it's mostly gas, but we'll try to build a tunnel from the North Pole to the South Pole. And we could start out with Earths, and to cover that tunnel, the diameter of the sun, you'd need 100 Earths. So the sun is a factor of 100 bigger than the Earth, and if you want to do that in terms of Einsteins, you'd need 700 million Einsteins. And we can take another step of 10 to the 2 or 100 and look at the moon, Earth's orbit around the sun. It's an ellipse, but it's not very elliptical. And if you average it out over the course of the year, you can replace it by an equivalent circular orbit. And to get an idea of the scale, so this drawing is not to scale, but to get an idea of the scale, what you can do is you can take 100 suns and put them in a row, and that'll reach from the sun to the Earth's orbit. So the Earth's orbit is 100 times the diameter of the sun. The diameter of the Earth's orbit is 100 times the diameter of the sun. And if we go back to our old system of units in terms of meters, it's this fantastically huge number here. And people who study the solar system don't want to use the meter as the length scale. So they use two different length scales. One's called the astronomical unit, and that's abbreviated the AU. And that's just the average radius of the Earth's orbit around the sun. That's 1 AU. The other unit is just to measure the time it takes for light to travel from the sun to the Earth. So light has perfected cruise control. So those of you who have cars with cruise control know what that means. You can hit a button and that car will go at exactly the speed you set it at. And so if you set it at 50 kilometers an hour, and you travel for an hour, you've gone 50 kilometers. And so you can say that you've traveled for an hour, and that's equivalent to saying you've gone 50 kilometers. And the same thing's true for the light. Light has perfected cruise control, and it travels much, much faster than cars. And up here is the speed of light in meters per second. It's 3 times 10 to the 8. And it's sometimes useful to think about this in slightly different units in terms of feet per second, because a meter is about 3 1/3 feet. And if you multiply 3 1/3 feet by 3, it's roughly 10. And so that's 10 times 10 to the 8 feet per second, or 1 billion feet per second. So light travels 1 billion feet in a second, or in a nanosecond, in a billionth of a second. That's the distance light covers. It's very, very fast. So we can divide this distance by this speed, and we get 500 seconds. And so if I tell you the sun is 500 seconds away, that's the same as telling you it's 1.5 into 10 to the 11 meters away, or it's 1 AU away. And so it's useful to measure distances in light travel time. So we can now take another step and go to our next nearest star, which is Proxima Centauri. And that guy is 4 times 10 to the 16 meters away, or in light travel time, it's 4 years away. And if you want to write that distance in AUs, it's roughly 200,000 AUs, or 2 times 10 to the 5 AUs. So the AU, again, is not that useful when you start study collections of stars, because you're getting huge numbers again. And so people who study collections of stars introduce a new length unit. And that's a little strange unit, so I'm going to try to explain it in terms of this cartoon diagram over here. So what that unit is you take this 1 AU here, which is a huge distance, and you take an astronomer and give her a telescope and ask her to go very, very far away. And you ask her to go so far away enough that this huge length scale, this linear length scale, subtends an extremely tiny angle at her. And you want that angle to be 1 arc second. So if you go around a whole circle, you cover 360 degrees. And each degree you can split up into 60 arc minutes. And each arc minute you can split up into 60 arc seconds. So a circle contains 360 times 60 times 60 arc seconds, which is roughly 200,000 arc seconds. So it's 1/200,000th of a whole circle, so it's a tiny angle. And she'd have to be really far away for this huge length to cover such a tiny angle at her. And when she's that far away, she's 1 parsec away. And that parsec is also an abbreviation. It's an abbreviation for a parallax of an arc second. So it's also abbreviated further down to a PC, and that's the length unit people who study collections of stars use. So we should kind of think about this a little bit. So when we say that the sun is 500 seconds away, That means when you're looking at the sun, the light that came off the photosphere, and if you look at the sun, you should always use protective equipment, otherwise you damage your retina. So that light that came off the photosphere took 500 seconds to reach you, to reach your retina, and get converted to an image in your brain. And that means you're not seeing the sun the way it is now. You're seeing the sun the way it was 500 seconds ago in the past. And this happens even in this room. So if you look to the person on your left or your right, they're roughly about 2 feet away. So you're seeing them 2 nanoseconds in the past. You're not seeing them in the present. But your brain doesn't really care about nanoseconds, so it automatically assumes you're seeing someone in the present. So you've got to really think about this carefully when you're thinking about stuff on very large scales. So when you look at Proxima Centauri, you're seeing it 4 years ago in the past because light was traveling from there and it took a long time to get to you. And we can make this a little bit more concrete with examples we're probably more familiar with. So the Earth-Moon distance is 4 times 10 to the 8 meters, or it's roughly 1 1/3 seconds. And that's the furthest humans have gone. So that's a tiny, tiny fraction of even the distance to the sun. And if you want to characterize something that gives you the size of the solar system, maybe you can think about Pluto's orbit, and that's 6 hours from us. So it's much further than the sun. And Voyager 1 and 2 are the furthest we sent things. And these were both launched in 1977. So these numbers are from the 40th anniversary in 2017. At that point, Voyager 1 had gone 19 1/3 hours in light travel time. And that's the furthest humans have gone. And the next nearest star to the sun is 4 years ago, and it's not even gone 1 day in 40 years. So we can go out to something even bigger, and this is our Milky Way. It's the galaxy we live in. It's a collection of maybe 150 billion to 200 billion stars. And the typical star is probably half as massive as the sun. And this is the most recent montage of photographs. It's a really beautiful image, and it's from the European Southern Observatory. So if you go to your favorite search engine and look for European Southern Observatory Milky Way, you can find this, and you can zoom in and look at parts of it, and it's a pretty incredible image. So this is the image we had 40 or 50 years ago with the older technology, and this is probably the best one to discuss. So this is the artist's impression of the Milky Way. So it's like a disk, it's like a frisbee, and if you look at it from the top or the bottom, you can see the spiral arms where the bright stars are, and it's just a circular disk. The central region has a bulge, and that's called the central bulge. The sun is about 1/3 of the way out. So I've got the diameter of the disk here, and that's 50 kiloparsecs, so 50,000 parsecs. And if you want to turn that into light travel time, you take that 50,000 and multiply it by 3 1/4 light years, which I forgot to tell you. So the most useful thing about parsecs is that a parsec is 3 1/4 light years. It takes 3 1/4 light takes 3 1/4 years to travel a parsec. And you take that 50,000 parsecs and multiply it by 3 1/4, and you get about 160,000 years. So if you could travel at the speed of light, and you can't, but if you could, and you started here, it would take you 160,000 years to cross the Milky Way disk. And that's huge compared to even the distance to the nearest star, which is 4 years from the sun to Proxima Centauri. The sun's 1/3 of the way out. And there's the nucleus here right at the center where a black hole lives. So that black hole is about 4 million times as massive as the sun, but it's actually pretty puny on the scale of black holes at the centers of galaxies. Most galaxies have black holes that are close to 1 billion times the mass of the sun. So this is embedded in what's called the halo, which is probably 10 times as big. And it's mostly dark. It doesn't have a lot of stars. And a lot of the dark matter is in the halo. And in the halo, we have collections of stars called globular clusters. These are collections of hundreds of thousands to maybe a few 100,000 stars. These are very old, and they've arranged themselves spherically around each other, and they make a spherical ball-like collection, and they kind of orbit the galaxy center in 3 dimensions. So some of them come out of the plane and into the plane, and some of them go in the plane. And you can see these objects if you know where to look. And I don't know whether they're amateur astronomy groups in Bangalore. I think at the planetarium they have telescopes. And if you haven't seen the Milky Way or globular clusters, you should try to do that because they're pretty spectacular. So we can go to our next nearest neighboring galaxy. This is the Andromeda galaxy. It's also a spiral galaxy, and you can see the spiral arms. And you can see the central bulge, and you can see the disk. And it's a little bit bigger. It's 60 kiloparsecs in diameter, so maybe something that could travel at the speed of light would take 200,000 years to cross it. And Andromeda, excuse me, is 750 kiloparsecs from us. And if we turn that into light travel time, it's about 2.5 million years. So when you look at Andromeda, and if you haven't looked at Andromeda, you should, because you can see it on the sky, and it's pretty spectacular. It takes that light from maybe a star in Andromeda or a hot gas cloud to travel in a straight line for 2.5 million years to come and hit your retina. So it left 2.5 million years ago. And that's an interesting time scale for human evolution. Probably the most famous hominin fossil is Lucy. And she lived in Ethiopia approximately 3.18 million years ago when one day she climbed up a tree, apparently to escape predators. And she probably fell asleep and fell out of the tree and killed herself 3.18 million years ago, which is a little bit longer, a little bit before the light that you see now from Andromeda left Andromeda. But that's millions of light years. And we can step out even further. And galaxies, because they're so massive, they're hundreds of billions of stars. And if they come near each other, Newton told us they're going to pull on each other and going to start orbiting each other. And they form these massive collections of galaxies with tens, hundreds, or thousands of them. And in the richer collections, they're called clusters of galaxies. And this is the center of a famous cluster called the Virgo cluster. And you can see probably 1,500 to 2,000 galaxies here. Every spot of light you see is a galaxy, and each of these has 100 billion or 200 billion or 300 or 400 billion stars. And you can see some that are closer by. You can see spiral galaxies and elliptical galaxies. And the scale here is a few megaparsecs. M tells you it's 1 million. So if you want to convert it to light travel time, you multiply a few million by 3.25, so maybe it's 10 million. And so it would take roughly 10 million years to cover this distance at the speed of light. And you can compare that to the 2.5 million from Milky Way to Andromeda and the 4 years from Earth to Proxima Centauri. So this is a pretty big object. But it's pretty small on the scale of the universe. So if we go out here, this is a larger scale picture. And we can set the scale here. It's 300 million parsecs across here. So that's 300 million multiplied by 3.25. It's roughly 1 billion. So 1 billion light years across here. So if you could travel at the speed of light, it would take you 1 billion years to cross this. And this picture was put together from images collected by these two people, Shane and Virtanen, who worked at the Lick Observatory, which is in the foothills, in the hills outside of San Jose in the San Francisco Bay Area. And they did this in the 60s before there were CCDs. So they would take big glass plates and put emulsion on them and stick them at the focus of the telescope and then develop them. And they didn't have access to scanners or computers. And so for those of you who sometimes worry about your homework, it's really interesting that these two guys sat there with paper and pencil and looked at these glass plates and figured out the angular positions of 400,000 galaxies by hand. And that's where this image came from. It's kind of smoothed out a bit, so it's not, you don't really see 400,000 galaxies. But there's a lot of galaxies here, and you can see clusters of galaxies. That's the Coma cluster, which has maybe 7,000 or 8,000 galaxies in it. And that's just a few pixels on this image. You can see other clusters of galaxies, and they're not huge objects here on the scale of this image. And if you look closely, you can see a couple of other objects, types of objects. You can see regions that are dark, and those guys are called the voids. And they're regions where they don't have too many bright galaxies. And you can also see one-dimensional filamentary structures, which are called filaments. So the easy way to think about this is to think about soap bubbles in your basin. And the interior of the soap bubbles are where the bright galaxies tend to avoid. They tend to congregate more on the surface of the soap bubbles. And where two soap bubbles come together, there's an enhancement in the number of bright galaxies. So when you see that projection, it looks like a one-dimensional line, and there are more bright galaxies over there, so the filaments stand out. And the filaments tend to drain into, very loosely, into the clusters of galaxies. So this is called the cosmic web, and it's how matter is arranged on scales of hundreds of millions of light years. And this is something that's known as anisotropic. So when you say something is isotropic, you're standing at one point and you're looking around you in all directions and it looks the same. So in this room, when you look to your right and you look above you, you don't see the same person. This room is very anisotropic. And if we go up 100 kilometers from the surface of Bangalore and look out and you look to the west, you'll probably see the ocean, and you look to the north, maybe you can see the Himalayas there. And it looks very different depending on which direction you look in. The surface of the Earth is very anisotropic. The solar system is very anisotropic. You look in one direction and you see the sun, and you look in any other direction, you don't see an equally big nearby star. And the Milky Way is anisotropic, and it's anisotropic on scales of tens of millions of light years. So that's not that surprising. The thing that might be a little bit more surprising is when you go out another factor of 10 or so in length scales, it becomes very isotropic. And this is the afterglow of the Big Bang. This is a picture that was put together by measurements from the European Space Agency Planck satellite, and it shows you the cosmic microwave background radiation anisotropy. A lot of really big words. So what it is a satellite with a detector that looks for microwaves. And if you use a microwave oven at home, you know what microwaves are very approximately. They're part of the electromagnetic spectrum, but they're much, much longer wavelength than the wavelength that you see with your eyes. And these guys, the wavelength's probably from a fraction of a millimeter to a millimeter or 2 millimeters or so. So they're something that you can touch those length scales with your hands, but that's the wavelength over here. And so they had this satellite out there, and the satellite had the detector, and it was pointing in all 4 pi solid angle and catching the electromagnetic microwave radiation that was coming down from the cooling Big Bang towards it. And so what we have is, we can think of a big beach ball out there, and that it was basically looking at the color of the surface of this beach ball after that electromagnetic radiation had propagated towards it. And we can tell from the color of light what the temperature of that light was. And so this is color-coded in terms of temperature. So the hotter temperature is the red spots, and the cooler temperature is the blue spots. And so we've taken this balloon, this beach ball, and sliced it from the North Pole to the South Pole and opened it out. And if you want to reassemble it, you take this edge and fold it up and put yourself in the center and fold it around you. And so we're just measuring the effective temperature of the surface of the interior of the beach ball. And so maybe you're interested in the average temperature. And so if you average this temperature, it turns out to be roughly 3 Kelvin. So Kelvin is the absolute temperature scale, and that's what physicists and engineers use. And to make that more concrete, this room is roughly at 300 Kelvin now. And so 3 Kelvin is very, very cold. So this is a very cold set of electromagnetic radiation. Once we know the average, we might be interested in how bumpy this is, how much less than average the blue spots are, and how much more than average the red spots are in temperature. And the temperature difference between the red spots and the blue spots is roughly 30 millionth of a Kelvin, 30 microkelvin. So if you want to compare the bumpiness, the 30 microkelvin, to the average, which is 3 Kelvin, you divide the 30 microkelvin by 3 Kelvin, and you get 10 to the minus 5. Or if you turn that into a percent, it's 0.001%. So the temperature over here is the same as the temperature over here, and it differs only by 0.001%. So this is very isotropic. No matter what direction you look in, it's roughly the same temperature, which is very, very different than even on these scales of tens of millions of light years, where it's very different. If you look over here, you see some bright galaxies. You look over here, you see hardly any bright galaxies. So these are two really, really important facts about the universe, about reality, that on small scales, locally in our neighborhood, matter and light are distributed in a spatially anisotropic way. They look different in different directions. But when you get out to large scales, on scales of tens of millions of light years or greater, in an average sense, the matter distribution and the light distribution and various other radiation distributions are isotropic in space. And I'm not going to talk more about these two facts here, but if you're interested, physicists try to make sense of this in what's known as the inflation model of the very early universe. And you could look on reputable websites like Wikipedia or Scientific American or Physics Today to learn more about the inflation model of the very early universe. And that model makes some predictions, and those predictions are not inconsistent with the observations that we have. But the observations we have are not precise enough to conclude that the inflation model of the universe is really what happened. And that's something that happened when the universe was maybe 10 to the minus 33 seconds old. The universe now is about 13¾ billion years old. So it's much, much older than when inflation happened. So we got over the really simple facts about reality. Let's move on to something a little more complex. And that's that the universe expands. And so if the universe is expanding, we have an implicit understanding that we must have measuring devices that are not also expanding in exactly the same way. Because if our measuring devices were also expanding with the universe, we wouldn't know the universe was expanding. And so it's kind of important to try to understand why our measuring devices might not expand. So on the scales of our measuring devices, I have a toy one here, a centimeter stick, and it's got marks on it and tells you a length scale. And on the scale of this object and on the scale of the universe, there are only really two forces that are important. So one's gravity. So if I have a mass and I don't support it, it's going to be attracted by the Earth's mass. And it's also going to pull the Earth towards it, but the Earth's going to pull it down. And we know what the law is. It's called Newton's law of gravity, the inverse square law. And that tells us that the force on each of the masses is proportional to their mass. And it's inversely proportional to the distance between them squared. So the distance squared comes in the denominator. So if you double the distance, if you go from r equal to 1 to r equal to 2, then that's 2 squared, and so the force goes down by a factor of 4. If you triple the distance, the force goes down by a factor of 9. And the only other thing that appears there is Newton's big G, his gravitational constant. So that's the gravitational force. It's always attractive. we're made up of charged particles that are collected together in things called atoms and molecules. But if you break up atoms and molecules, you'll find a nucleus that has things called protons and neutrons, and then you'll find an external electron cloud. And conventionally, the electron is said to have a negative charge, and the proton is said to have a positive charge. And those guys interact through the electric force. So if you bring two electrons close together, they don't like each other, and they get pushed apart. And the same thing happens if you bring two protons together. They don't like each other, and they get pushed apart. So they get repelled from each other. But if you bring an electron and a proton together, bring two objects of different charges together, they get attracted. So the electric force can be attractive between unlike charges, or it can be repulsive between like charges. And it's also an inverse square law force. So you double the distance, it goes down by a factor of 4. And you triple the distance, it goes down by a factor of 9. And the law that describes electric force has a name. It's called Coulomb's law. And it's somewhat similar to Newton's law for gravity. The difference is that these two forces are very different in strength. So if we take two protons, and they're going to be repelled electrically, and they're going to be attracted gravitationally. And so we can compare the repulsion to the attraction. And if you do the algebra, you find out that the repulsion is 36 powers of 10 stronger than the attraction. So gravity is a very, very weak force, and the electric force is a much, much stronger force. So I have a few more questions for you. You can put up your hands to answer them. So how many of you think you're pulling your neighbor towards you gravitationally? If you think you're attracting your neighbor gravitationally, put up your hand. So maybe 1/3 of you. How many think you're repelling your neighbor gravitationally? Nobody? So 2/3 of you didn't answer. What do you think the answer is? I guess you're just shy. So you have protons and electrons in you. So how many of you think you're repelling your neighbor through your electric force you exert on your neighbor? 1, 2, 3, 4, 5. How many think you're attracting your neighbor through your electric force on your neighbor? 1, 2, 3, 4, 5. I guess most of you are really shy and don't want to answer. So I don't think you're either attracting or repelling your neighbor through the electric force. I mean, unless you vigorously combed your hair before you came here or you biked in. So you're neutral. You're made up of atoms and molecules. So an atom has a nucleus that has a certain number of protons of positive charge, and it has an electron cloud that has electrons, and it's the same number of electrons that has protons. So your electrons are pushing your neighbor's electrons away, and they're pulling your neighbor's protons to you. And those forces exactly cancel out because you're neutral. So if you build up some charge, and you can do that by combing your hair vigorously, then you change the equation a little bit, and then you can either attract or repel your neighbor. But the gravitational force between you and your neighbor is positive. You're pulling your neighbor to you gravitationally. And if you scale it up to two planets sitting next to each other, it's a much, much stronger gravitational force. And you scale it up to two galaxies, it's much, much stronger than between two planets. And so as you go to larger and larger scales, matter becomes neutral in the bulk. And there's no electric force, but the gravitational force becomes stronger and stronger. So as you go to larger scales, gravity is more important than electromagnetism or electricity. And on the scales of this ruler, it's held together by the electric force because it's made up of atoms. Those atoms have electron clouds. Those electron clouds don't like each other, and they try to push apart. But they can't go anywhere because they have other atoms on the other sides of them. And so all the atoms are pushing against each other, and that gives this matter rigidity. But on the scale of the ruler, the gravitational force is very, very weak. But when you get out to the scale of planets, they're made up of atoms, and there's almost no electric force between planets. I mean, you can have some charged particles, but it's not significant. The gravitational force is much more important on large scales. So if you want to talk about cosmology, you have to talk about the most accurate model we have for gravity, which is Einstein's theory of general relativity. And that came about as an improvement on Newton's picture of gravity. So Newton started out in the 1600s by assuming that space was fixed and time ran uniformly, and he could do all his experiments in this fixed space. He could collide his balls, and that it wouldn't affect the time and it wouldn't affect the space. And then in the early 1900s, Einstein realized he could give a better description of reality in certain cases, especially when the objects were moving at speeds close to the speed of light, or he was talking about very, very large length scales, or he was talking about very strong gravitational fields. If he could make space and time be part of the dynamics of the physical system, so when the balls were moving, space and time would deform. And that's the model we have to use for describing how gravity behaves on very large scales. It's called the general theory of relativity. And very loosely, in some sense, it's just a collection of partial differential equations, nonlinear partial differential equations that describe how the metric tensor changes in response to how the mass distribution changes. And it also describes how the mass distribution responds to the metric tensor. And there's not much point in me writing down all the solutions here and showing you the mathematics. So usually what people try to do is they try to translate these solutions into English and then describe them in English words. And that translation is very inexact. And so I'm going to try to do this in English, and then you've got to remember that it's inexact. And so the first thing that happens is that general relativity wanders around space. I mean, this is just for the cosmology part, so I'm not talking about black holes or something, so the description's a little bit different there. But when you're doing cosmology, general relativity wanders around space, and it looks for underdense regions on average, and it creates more space there. And everything lives in space, and that extra space has to go somewhere, so it travels around, and it pushes out, and everything lives in space, and that stuff goes along for the ride. And that's the expansion of the universe. Excuse me. So I have a couple of demonstrations of maybe something that might make it a little bit easier to appreciate. So I have a one-dimensional space here, so I'm just asking you to ignore this width and just focus on this length here. And if I set up an origin here, I could mark off distances, and I just have one coordinate, and I just need one number to know how far I am. And this is going to be part of my expanding space. And I've got a measuring device here, and I've also got a wave on this expanding space. And it's got a wavelength, and you can see the distance between two peaks in the wave, or two troughs in the wave, and that's the wavelength. And my measuring device is held together by the electric force. But what general relativity is going to do is it's going to create more space, and that space has to go somewhere, and it starts spreading out. And the wave lives on that space. And so what happens is that the wavelength gets bigger and bigger as more and more space is created. If you have a contracting universe, the wavelength gets smaller and smaller. Okay, so that's one sign that we might be living in an expanding universe if you find that the wavelength is changing as a function of time. And maybe one way to interpret that is to think more about the frequency or the pitch. And you've seen this phenomenon, a related phenomenon very loosely, called the Doppler effect. If you've noticed what happens when a police car or an ambulance goes by you with the siren on, as that approaches you, the pitch goes up and the wavelength goes down. And as it recedes from you, the pitch goes down and the wavelength increases. And so when the wavelength increases, in physics, we talk about short wavelength light, and we call that blue light. I mean, blue light is shorter wavelength than red light. So when something's receding, the light is red shifting from you, and when it's approaching you, it's blue shifting. There's a couple of problems with this demonstration. So first of all, there's probably no end to the universe, and general relativity doesn't start grabbing the ends and pulling. So the universe, in the simplest model that's consistent with the observations, the universe is infinite in space. So it's actually a three-dimensional space. So we have a vertical dimension here, and there's a two-dimensional plane on the floor here. So if I set up my origin over here, and I want to know the position of my finger over here, I'd have to measure the distance from that wall, from the floor here, and from some back wall here. So I'd have to give you three numbers. So it's a three-dimensional space. And that's our space. We live in a three-dimensional space. But this is a one-dimensional space. So it's probably infinite in extent. The simplest model we have that it fits all the observations has an infinite space, infinite in all three dimensions. And so it's not pulling on the edges, but it's going into space, and it's creating new space and pushing it out. And let's move on to the next one, because I think I'm starting to run out of time. So this is a picture of what I was just demonstrating to you, but we can look at a couple of other things here in the context of this slide. So we start out at an earlier time. The hands are closer together, and then I stretched it, and the hands are further apart. And you can take an exercise band like this and draw a wave on it, and you'll find that the wavelength, the distance between the two peaks, gets bigger in proportion to how big the space gets. So the wavelength is always going to be a fixed fraction of the distance between the two hands. And one loose way to describe the size of the universe is to say that the size of the universe is the distance between the two hands. And cosmologists would call that the scale factor, and the symbol they use for it is A, and it's a function of time. So as time changes, A changes, and that's what this symbol denotes. So as time goes on, A gets bigger, so time gets bigger as you go forward, go down this way, and the wavelength gets bigger, and the distance between the hands, or the scale factor, gets bigger. And the wavelength, if it starts out at blue, it can get red or red shifted. As the rubber band stretches, it gets redder and redder. So astronomers don't like using the scale factor, but they use a different variable, which they call the redshift. And the redshift is this variable z, and it's defined this way: 1 plus z is equal to the value of the scale factor now, the value of the distance between the thumbs now, divided by the value of the distance between the thumbs at the point when that light you're looking at now was first emitted. So it's just the ratio of this distance to this distance. So if you emit the light at the present time and detect it at the present time, then A of t would also be A of now. And so A now divided by A now is 1, and Z would be 0. So the redshift is 0 here, but as you go back in time, the denominator gets smaller and smaller, and the right-hand side gets bigger and bigger than 1, and so Z gets bigger and bigger. So while time increases downwards, scale factor increases downwards, wavelength increases downwards, redshift increases upwards. This is 0 redshift, and objects that are in the past are at higher redshift. So this is the expansion of the universe. And this guy was the first guy to discover this redshifting. So he was working at Lowell Observatory, which is in Flagstaff, Arizona, about maybe 80 kilometers south of the Grand Canyon. So if you have ever been to Grand Canyon, you had a chance to visit this, or if you go to the Grand Canyon, you should go to Flagstaff, and you can get and look at Lowell Observatory. You can get a tour of this telescope and other telescopes there. So he uses telescope. This is Slifer. He uses telescope to collect light from galaxies outside our galaxy, put that light through diffraction gratings, so you can think of it in terms of prisms, to break it up into its spectrum. And he identified spectral lines. So from the ratios of the wavelengths of the spectral lines, he could tell what atoms or molecules were creating that light. And then he collected those atoms and molecules in his lab, and he measured the spectral line wavelengths. And he found that the wavelengths he was seeing in these distant galaxies were larger than the ones he was seeing in his lab. So he was seeing redshifting. And so one thing he could have concluded was that at some time in the past, in the same point of space where he was now, there was a big explosion, and everything started moving away from him. And because of the Doppler shift, he was seeing the redshifting. And that's not what happened. What happened was something even more interesting. And maybe I'll start with this demonstration. So I have ping pong balls here on an elastic band. And the ping pong balls are supposed to represent fully formed galaxies. So galaxies, after they are formed, they do not get affected by the creation of space. They remain the same size. So what's happening is that the space between them is being created, and they're getting separated in space. And if you look at this three-dimensional version up here, it's the same as that pretty much. But we have a three-dimensional chunk, and my galaxies are the chocolate chip cookies here. So it's a three-dimensional space. There's a vertical dimension, two horizontal dimensions. And I told you earlier that everything is distributed isotropically in space. So if you go out over here and look at the edge and look outside, it's going to look different than the inside. So this cannot describe our universe. So it's got to be isotropic, and the only way you can make this isotropic is to send the edges out to infinity. And if you send them out to infinity, you have no edges to look out of, and no matter where you're looking, you always see the same thing, and it's isotropic. So if you have to think about this, you have to think about it as an infinite cake or an infinite loaf with chocolate chip cookies with an infinite number of them representing galaxies. And we'll put an observer on each of these chocolate chips, and we'll let the yeast rise and keep rising. And we'll ask the observer on 1 what she sees, and she'll tell us she sees every galaxy or every chocolate chip moving away from her, and we'll ask the observer on 4 what he sees, and he'll tell you exactly the same thing the observer on 1 told you. He's going to tell you every galaxy he sees is moving away from him. So the fact that Slipher saw things moving away from him didn't mean he was at the center of an explosion. This is actually the correct description. And the next thing that happened is that Hubble came along with a bigger telescope, excuse me. And this is Hubble and the telescope he had access to then, which is on Mount Wilson in the San Gabriel Mountains, north of the Los Angeles Basin. You can also get a tour of this telescope if you're interested. So it's 100-inch. It has a much bigger mirror, so it could resolve fainter objects. And he saw individual stars in some of the galaxies Slipher had looked at. And he would look at these galaxies over and over again, and he realized some of these stars were pulsating. And he identified some of them as Cepheid variable stars. And perhaps the most famous Cepheid variable star is Polaris, the North Pole star. And these guys are very, very useful because of a discovery that Henrietta Leavitt had made, I think in 1907. She was based at the Harvard-Smithsonian Observatory in Cambridge, Massachusetts. And over there, astronomers would send their glass plates. So she had access to many, many of these glass plates. And if you know astronomers, you'll know some of them are pretty obsessive. And they take pictures of the same region of the sky over and over and over again. So she had access to images of the same region of the sky 50 or 60 different times. And so she could see pulsating stars in them. In some of the images, they were really bright. In some of them, they were really dim. And she realized these were Cepheid variable stars. And so she went and measured the distance to some of the nearby ones. And from there, she could figure out the pulsation period of these stars are proportional, are related to how intrinsically bright they are. So if you know how they pulsate, how many times a minute or day or hour they pulsate, you can figure out their wattage. And that's called the absolute luminosity. And once you know the wattage of something, you can figure out the distance, because that star puts out that energy and it spreads it out over space, and it spreads it out on the surface of a sphere. And you can detect a little bit of it, and you can use the inverse square law to measure the intrinsic luminosity, compare the absolute luminosity to what you measure, and you can get the distance. So Hubble could find these pulsating stars, and he could measure the distance to these galaxies. And what he found was this really nice law, the recession velocity. So this is what Slipher got from the redshifting of the spectral lines and Doppler's formula. And Hubble measured the distances, and he found this linear relation between the two of them. So a galaxy twice as far away would move as twice as fast. A galaxy 3 times as far away would move as 3 times as fast, and so on. And we can look at an image, a plot here. So this is the plot of the final Hubble Space Telescope measurements of the key project. One of the key projects was to measure the Hubble constant more accurately. That's what the Hubble Space Telescope was built for one of the things. And this was the group led by Wendy Friedman, and this is their final paper from 2001. And you can see the recession velocities plotted on this axis. This is 10,000 kilometers a second, 20,000 kilometers a second, 30,000 kilometers a second. And on this axis, we have the distances. So a galaxy 100 megaparsecs from us is moving away at 7,000 kilometers a second. A galaxy 200 megaparsecs from us is moving away at 14,000 kilometers a second. And this red line was the best fit to the data then. And that gave us a Hubble constant of 72. And the value hasn't changed. It's dropped a little bit. And my favorite value is around 68 now. So that's the expanding universe, and maybe I can show you, so how much? 5, okay. So I'll kind of back up, and if there are questions, we'll go over them. So I'm going to show you a two-dimensional expanding universe, and it's going to take a little bit of time to fill this balloon, but you have to think of yourself as a little ant that lives on this balloon. And all you can do is walk on the surface. You can't go inside the balloon. You can't come out of it. And these galaxies are my red dots. My red dots are the galaxies. They're stuck on. They're pieces of paper. They're not being expanded with the creation of space. Space is being created in between the galaxies. So it's a two-dimensional object. Excuse me. If you just look at the surface of the balloon, it's like the surface of the Earth, and if you know the latitude and longitude, you know where you are on the surface of the Earth. And you can just walk on it and just explore things. And so while this is expanding, maybe I'll talk a little bit about what you can observe here. So if we look at a given galaxy, and we sit here with our telescope, and we look at this nearby galaxy, this galaxy might emit blue light traveling to our galaxy over here. And because there's a very small separation here, as time goes on, that blue light goes through an expanding space, and its wavelength gets stretched, and it gets a little bit redder. But if you look at a further away galaxy, that distance is larger, and it takes longer for that light to reach here, and space has created a bit more space, and it's redder. And if you start over here, it takes even longer, so it's even redder. So the further away the galaxy, the redder it is, and as time goes on, you just create more and more space. So you should ignore this neck, but everywhere else, there's no preferred point on this. Any observer on here would, on average, see faraway galaxies are isotropically distributed on the surface, and they're all moving away from that observer. So that's another toy demonstration of the expansion of the universe. We can let it go for a little while. And we have an expanding universe. So I'll just kind of skip this one, and we can come back to it if there's a question. So we know that the universe is expanding because Sly foresaw things are redshifting, they're moving away from him. And so there's an expansion rate, and the expansion rate, it's a time derivative, it's a rate of change divided by the scale factor, the rate of change of the scale factor divided by the scale factor. And we know things are moving away, so the person who's powering the universe had started it off and started moving away because they're redshifted. Then we might ask how she's going to proceed after that. Is she going to hit the brake pedal, and is she going to slow down and eventually come to a stop? Is she going to decelerate? Or is she going to hit the accelerator, and is she going to start speeding up, and is she going to move away further? And to do that, it's useful to get an acceleration equation. So 1 dot is the speed of the expansion, 2 dots is the acceleration of the expansion. And we know what force is responsible for this, so it's gravity. So what we're going to do, instead of talking about the whole universe, because gravity is caused by mass, so we'll focus on a little area and see how much the mass in here creates more space over here. So instead of talking about the mass of the whole universe, I'm going to take the mass divided, you should really think of a three-dimensional universe, the mass divided by the three-dimensional volume. And that's a density, it's mass per unit volume. So you can get this equation that tells you that the acceleration is proportional to 4s and pi's and 3's. That's kind of unimportant. But there's Newton's big G over here, and there's a negative sign over here, and there's a bunch of stuff inside the square parentheses. So I'll start out with the simplest thing, with the matter, and that's the dark matter and the atoms, and that's the density of matter. It's the mass per unit volume. So if you just have a bunch of galaxies out here, and we can think of this in terms of how Newton would describe things. So these galaxies are going to pull on each other, and if they're close enough to each other, their force is going to be stronger than the force that creates the space that Einstein uses to give you the expanding universe. And they'll pull on each other, and they'll slow down the expansion, and eventually they might lead to a contraction. So you can see that all here in the math, that because of the minus sign, you get a deceleration. It's not an acceleration. It's a slowing down when you have ordinary matter. And this is a relativistic effect. I'm just going to go through this really quickly. So these galaxies are really not stuck on the surface of this balloon because they're going to be influencing each other gravitationally, and they're going to be pulled towards each other, and they're going to be moving on the surface. And I can't give you a demonstration showing you that on this balloon, so I just stuck them on here. But if they're moving, they have a speed, and if they have a speed, they have an energy of motion. So there's an additional energy in addition to the energy associated with their mass. And that energy of motion, we know from Einstein, for any energy, E, there's an equivalent mass, which is just the mass times the speed of light squared. That's his famous formula, E equal to mc squared. So if you have this energy of motion, there's an associated mass. And in terms of a mass per unit volume, that becomes a pressure. And that's why I have a P here. And there's a 3 because there's 3 dimensions of space. So pressure is positive for ordinary matter, for galaxies, for atoms and molecules. And this guy remains positive inside this round parentheses. So even if you have moving galaxies, there's a deceleration. And so you're really happy. You've made a really strong prediction that Einstein's general relativity leads to decelerated expansion. And so you go and tell your astronomer friends, go and measure a double dot, and you'll find it negative. And so they go and measure it, and they come back and they tell you that a double dot is actually positive. So you're stuck with the problem. You can either conclude that this equation is wrong, and so your reasoning was incorrect because you used the wrong equation. And we don't want to throw away Einstein's theory of general relativity because we know it works really well for black holes. We know it works really well for gravitational waves. And so we want to try to patch it up and see if we can introduce a hypothetical substance to resolve this issue. And so we introduce another substance which we call lambda, and it has an energy density, it has a pressure, and it's the same kind of form as you have over here, except instead of the m's, I have a different subscript. And what I'm going to do is I'm going to give the lambda a different kind of pressure. I'm going to say its equation of state is such that its pressure is the negative of its energy density. And so inside the second round pair of parentheses, rho lambda plus 3p lambda, if you replace the p lambda by minus rho lambda, this becomes minus 2 rho lambda. And then if you make rho lambda large compared to rho matter and p matter, this guy is negative and large, and it can overwhelm the positive aspects of the matter part. And then everything inside the square parentheses becomes negative. And then it can flip this minus sign because you have a minus sign times a minus sign, and it gives you accelerated expansion. And so this would be a really crazy thing to do, to introduce this hypothetical substance to fix this one sign problem. But it turns out when you measure dark energy, so this substance is called dark energy. It's called the cosmological constant, which is the simplest example of dark energy. It turns out when you try to measure the amount of dark energy using half a dozen different techniques that are independent of each other, they all agree that there's about the same amount of energy, dark energy out there. And so that kind of lends us hope that maybe we're on the right track. And with more and better data that we'll be able to pin down what dark energy is. And I better stop here before I get into trouble. Thank you. Okay, I'm happy to answer questions. I don't know if there's a mic somebody wants to pass around, or just whoever. Yeah, if you can put your hands up so you'll know.
Hello. Good evening, sir.
Good evening.
Good speech, by the way.
Thank you.
My question is rather simple. You say that the universe is expanding, right? What is it expanding into?
It's not expanding into anything. The universe is infinite, and it's the only thing out there, and it doesn't expand into anything. So the Big Bang is an instant in time in the past where you had an infinite space with an infinite number of points in it, mass points, and each of these points started moving away from every one of the other infinite points. So this infinite space is getting bigger and bigger and bigger, and it doesn't expand into anything. There's nothing outside of it.
Okay, and do you think dark matter plays a role in expansion of the universe?
Yes, dark matter also shows up here. So this guy includes atoms and molecules and the dark matter, and it behaves in a different way than dark energy, and it also is responsible for the expansion.
Thank you for a nice talk, sir.
Thank you.
My background is more like that of an informed layman to which all the popular science books are targeted. So my question is maybe not directly from your talk, but I've read that the particle physics estimates of vacuum energy, which is one description of what the cosmological constant could be, is off from the measured values by more than 100 orders of magnitude.
Yeah, so that's correct. So this is a problem that's related to how we deal with quantum mechanics and gravity together. So if you can measure this energy density, so this energy density is an energy per unit volume. So it's in the normal units we use, it's energy divided by length cubed. And in natural units, length is also proportional to 1 over the energy. And you can kind of appreciate that, because if you want to go to smaller and smaller length scales, you need to build particle accelerators that have more and more energy so they can probe smaller length scales. So length is inversely proportional to energy. So energy divided by length cubed is energy to the 4th power. So once you measure this energy density, you can take the 4th root, and the 4th root of that in units that you might not be familiar with, it's going to be about 1/100th of a milli-electron volt. So the transition in the hydrogen atom is about 13 electron volts. This is 1,000th of that, or 10,000th of that. So it's a pretty small energy. And that's the energy scale that's kind of associated with more with chemistry. And from particle physics, there is the vacuum is not completely empty. From the uncertainty principle, Heisenberg uncertainty principle, maybe not the, I don't know if you know the delta P, delta X one. There's also a delta E, delta T one, where you can violate energy conservation provided you do it for really short times. So you can create and destroy particle-antiparticle pairs. So it's kind of the sea of particle-antiparticle pairs. And you can add up the vacuum energy. And if you do that, it's roughly 10 to the 30 electron volts, 10 to the 30 milli-electron volts. So the ratio, it's the energy scale associated with the cosmological constant is 30 powers of 10, smaller than the natural scale you get from adding up these things. And when you raise that to the 4th power to get the energy density, that's where the 120 comes, because 10 to the 30 raised to the 4th power is 10 to the 120. So the natural scale you expect, and so this is kind of a definition of natural, and I'll come back to that. In quantum field theory, is to be 30 powers of 10 larger than what you measure through these experiments. And this natural scale is called the Planck scale, and it's where quantum mechanics and gravity are equally important. And unfortunately, we have no description, mathematical description that's consistent, that works when quantum mechanics and gravity are equally important. And so probably this is tied to understanding how you can properly quantize gravity. And maybe there's more to it than just that, but that's kind of the issue right now. In this model that breaks down, there's this 30 powers of 10 difference.
The emptiness of the space, is it part of the universe or it is outside the universe? This is a question which is a corollary to the earlier question.
Yeah.
What is it expanding into? If you say that there is not expanding into anything, is there some emptiness which is constantly being created? A space is being created?
Space is being created, and it spreads out, and it's not expanding into anything. There's nothing beyond the universe. I mean, it's a question you can ask, like, what's north of the North Pole? And there's nothing north of the North Pole, right? I mean, you could go on the surface of the Earth, and you can't go beyond that. So I mean, the universe is everything, and all you're doing is you're creating more space. You're making the distance between points bigger and bigger, and things just move apart.
So no new space is being created?
Space is being created. I mean, that's the English translation of Einstein's equations.
If the space is being created, what was there before it was created?
There was nothing there. It was the previous space. So what was here when I just stretched this?
Single dimension I can understand.
Yeah.
But this is three-dimensional situation.
So you can understand the two-dimensional thing, right? If just the surface of the balloon, it's the same thing.
The balloon is expanding into the room.
Yeah, but there's nothing there. No, you're not supposed to think of the room. You're a little ant, and you have no idea that there's anything outside the balloon or inside the balloon. And it's because of your perspective that you're in this three-dimensional volume that includes the two-dimensional balloon that you're seeing this. But if you're a little ant on the surface of this and you have no conception of what's out here or what's inside, all you have is a meter stick and a protractor, and you can measure the distance between points, and they get bigger and bigger and bigger, and you can't look into the third dimension.
I know that was I mean, not disappointing, but it's not intuitive for a human to grasp that concept.
Yeah. So we can go back to where I started. So that's why I spent so much time on this. So you can't access these length scales directly through your senses, and all your intuition has been built on what you get through your senses, unless you have an advanced degree in physics. And so your intuition is based on stuff that's happening over here. And if you go many orders of length away from there, you have no direct intuition of how it works. And you can collect the light, you can store it in a computer, you can make a mathematical model, make predictions, and if it agrees, then you're really happy. And general relativity works really well. And so the description of general relativity I gave you was an English translation of the mathematical equations, and that's an inexact translation. I mean, you know this even if you read a book in a different language and the translator's not good, it doesn't make sense, right? And so you have to learn the original language of the author and read it in that language if you really want to appreciate it.
Sure. Thanks. Well, that was not my question, sorry. I'm Manohar. This is my first time attending something like this live. Always been like watching such sessions on YouTube. So first of all, glad to be here. My first question is, you talked about dark energy and dark matter. At this time, I know that we don't have a great grasp on what that is or what those are, probably beyond our current understanding, and there is something out there that we don't know yet, or it could be something that already exists, but again, it's beyond our current understanding. So what is your take? I know for dark matter, we have some 3, 4, 5 theories, and for dark energy, I think there is 1 or 2.
Yeah, there's probably thousands of theories for dark matter and hundreds of theories. I mean, you shouldn't really call them theories, you should call them models. I mean, when they get established, then you can call it a theory. But we don't have a very good understanding of either dark matter or dark energy. And it's probably, for dark matter, they're probably particles, at least in some sense. And we do have some examples. So we have these particles called neutrinos that interact very weakly. And they were postulated by Pauli in the 1930s because there were collisions. And in these collisions, when you measure the stuff that was coming out, it seems they were violating conservation of energy and conservation of momentum. And Pauli says, we don't want to get rid of those fundamental principles. And so he said, let's introduce another particle, which we'll call the neutrino, and we'll let it carry away some of the energy and momentum, but we'll make it interact extremely, extremely weakly with our detectors. So unless we have much more sensitive detectors, we'll never see the neutrino. And so it took like 25 years to build a detector sensitive enough to even detect a neutrino. And dark matter, if it's made up of particles, it's probably even more weakly interacting than the neutrino. And these things started getting quantified maybe in the 1990s for the first time, so maybe in the last 3 decades or so. And we haven't seen any non-neutrino dark matter particles, because neutrinos behave like dark matter, but they don't give us enough of the dark matter, so there's got to be other things also. And dark energy is more difficult because with these neutrino experiments, you can do them in huge, huge labs on the Earth, but you don't see the effects of dark energy unless you're looking at distances of tens of millions of light years. And so it's a much more difficult thing to really pin down than even the dark matter. But hopefully, in the next 10, 20, 30 years, we'll get better measurements.
Dr. Batra, thank you very much. I really enjoyed your talk. First of all, took me back to my college days. The question I have is really about the point that you made about galaxies are moving away. And I understand that. I also remember studying that in college. What I'm still struggling with is that why aren't galaxies themselves expanding? And is that because there is some sort of an equilibrium within galaxies of gravitational force? Is that what the assumption is?
So the galaxies that are already fully formed are very consistent with Newton's description of gravity, and that 1/r² law gives you a strong enough force to hold those together. The space creation process happens. So galaxies, typical scales of galaxies, it's hundreds of thousands of light years. And the space creation process becomes significant on tens of millions of light years. And it's relatively unimportant on scales of hundreds of thousands
so
of
they
light
do
years.
expand, but relatively speaking,
No,
there is...
they don't. I mean, they're basically held together by Newtonian gravity. So but galaxies had to form first. So when they were forming first, they were much more diffuse and they were much bigger relatively, and gravity pulled them together. But if the galaxy initially, it was a gas cloud, if it was big enough, then the edges could be pulled out by the space creation process. But the central region could compactify and get more compact, and then it would be held together.
Okay, great. Thank you.
Thank you.
I have two questions. First thing, if energy cannot be created or destroyed, what is giving the universe energy to expand? And then if it was only from the Big Bang, then why is the universe accelerating in expansion?
Okay, so let's first think about your first question. So if you lift this guy up here, right, so it's in a gravitational potential well caused by the Earth. And if I let it go, it's going to lose some of the energy, right? So you understand that as it drops, it loses energy. So in some sense, you can kind of think of this gravity potential well storing that energy. And that's basically what's happening. So as the space is being created, the distance between particles is expanding, and the gravitational field's energy is changing. So the total energy in the gravitational field and in the matter distribution is constant. So the total energy doesn't change. But the gravitational energy compensates for the rest of the energy. And so if the universe just kept, so the Big Bang starts it off, and it gives it an initial push, and it keeps going. And if there's lots and lots of mass, then the neighboring galaxies are going to overwhelm the space creation process. And if you think about this guy, it's going to get to a certain size. That gravity between the neighboring galaxies is going to be at a maximum, and it's going to pull this back together, and it'll start decelerating. So on a closed geometry, you get an expansion. Every point starts moving away from every other point. It gets to a maximum size, and then it collapses and starts contracting. And that maximum size, I'm not talking about the radius, I'm talking about the circumference, because you have to measure that in the space itself, so it gets to a maximum circumference. But so if you have ordinary matter, that's probably what's going to happen. But when you put in dark energy, because of the strange way that pressure and the energy density are related, it effectively gives you an accelerated expansion, and that's why you need to introduce dark energy, because we know that the expansion is accelerated. And I hope that helps a little bit. You're welcome. So only one more or two more? One more question.
Hello, sir. I am Dev Kirti. Amazing speech.
Thank you.
So my question is that in all these YouTube videos, we see how they talk about the space-time continuum expanding, how gravity affects the space-time continuum. Basically, you put a cloth, you put something in it, and it falls down. My question, and I know it is wrong, it is extremely wrong on how we are deciphering it, because our mind cannot actually take up all that. But my question is, how, if in the case of a planet, if you drop it in a sheet, it falls down and it creates a gravitational field. So how does it affect for a black hole?
It's the same thing. I mean, if you want to think about it in that way, it's got a much bigger mass, so it'll pull it down much, much further and make a much more deeper potential well if you're talking about a two-dimensional sheet. And excuse me. And it differs because it makes the gravitational field so strong at some point that even light can't escape from the black hole, while that doesn't happen with the planet. So that's the event horizon for the black hole.
Sir, thank you so much for your talk. Quick question on this note that you have said,
Yeah.
and the motivation behind it, and how long do we have? I mean, how long does that ant have before?
You don't have to answer anything. The answers are at the bottom.
No, not
so,
the answer, sir. What was your motivation behind this?
So the motivation is so some people have this problem with appreciating the reality of human-caused global warming. And that's kind of even related to this over here because it's coming from atoms and molecules. So sunlight comes in, it hits the ground, and the second law of thermodynamics tells us that it's going to be some of it's going to be re-emitted at longer wavelengths, less useful energy. And it goes back into the atmosphere. And carbon dioxide and methane and some other molecules are very good at trapping this infrared radiation that's being emitted from the surface of the Earth that's created by the incoming sunlight. And so we're heating up the atmosphere, and it's going to be a really big problem for civilization, probably the biggest problem we've had to deal with ever. I mean, we can start seeing small effects now by changes in weather patterns. I live in Kansas, and the jet stream has been unstable for some time now, the last 10 decades or so. And it's been the last couple of winters have been the coldest ever because it's come down south. And we can see even when you heat up the atmosphere, you're heating up the surface of the ocean, and you're causing more water to evaporate, so there's more waters in clouds. And that comes in storms, and there's more intense rainstorms over much shorter periods, and it causes much more damage or much more erosion, much more flooding. And so we need to accept reality. So there are really good videos on this site that clearly explain in layman terms what global warming is. And so it's useful for a lot of people more to know that this is a real thing. And so I'm just trying to publicize this. And this is a friend of mine. He's a social scientist, a psychologist, and he's interested in studying how people respond to scientific facts. And it's not just global warming. I mean, we've seen this with many other things like COVID and other issues where people no longer seem to trust science. And that's very, very dangerous for a civilization that's getting to be so dense where you can spread viruses very, very rapidly. And so that's my motivation to publicize this, and I think it's a responsibility for any scientist to do this because it's a scientific fact. Thank you.